In today's lecture, I will explain about the superconductivity. So as we know, it is a low temperature phenomena, and the superconductivity was discovered by Cameron-Lagrange in 1911. By Cameron-Lagrange. In this phenomena, basically what happens, it has been found that the electrical resistance of some of the metals drop very close to the zero at a very low temperature. For example, if I will talk about the mercury, so you can see here, in case of mercury, here it is temperature on the x-axis, on the y-axis here it is electrical resistance. So what happens as we are decreasing the temperature? So at certain temperature, abruptly it falls close to the zero here at this point. So first of all, this behavior of superconductivity has been discovered in mercury. So around 4.15 Kelvin, the electrical resistance of mercury suddenly dropped to zero. So it's a low temperature phenomena. For example, how it is different from the normal conductor? We can see that superconductor, what speciality is there in the superconductor and how it is different from the normal conductor, you can see here. If I will talk about the normal conductor, so you can see in case of normal conductor, if it is a wire, the current is flowing here, this wire has certain resistance, so there will be losses here. So you can see the losses will be like I square R. As we know, in case of normal conductor, R is not zero. R have some specific values. So if R will increase, then the heat losses will increase. So if we want to minimize the losses, then we can do it that R should be decreased. If R will decrease, then the heat losses will decrease. Here, in case of normal conductor, we also have limitations on the current, that there should be some specific value of the current that we can, we had the need to control the current. Actually, if we increase the current and we increase the resistance, then what will happen? The losses will be maximum. So in case of normal conductor, the wire may be burn. So this may be the case of normal conductor. What happens in superconducting phase? In superconducting phase, here you can see that if the resistance is 0, then H is equals to I square R. If R is equals to 0, then there will be no heat loss. H is equal to 0. So once the current flow inside the wire, it will flow for thousands of years because there is no loss here in case of superconductivity. So this is the beauty of superconductivity. If we are comparing superconductivity to the normal conductivity or we are comparing superconductor to the normal conductor, so we can see the behavior here that in case of normal conductor, the losses are maximum. So we have our limitations that certain amounts of current can be flow inside the wire, in a wire. But here R is 0. There is no resistance in case of superconductor. So what will happen here? That the more current can flow inside the wire and there will be no losses in case of superconductivity. So this is the beauty of superconductivity here. Now, what is happening here? There are various applications of superconductivity. For example, if we want to make a magnets, here is the magnetic field, this is the current. So what is the value of B? B is equals to mu naught Ni. So N is the number of turns, I is the current. So if in case of superconductivity the current is more if I will increase, so B will increase here. So with the help of superconducting materials, we can create powerful magnets. Those magnets nowadays they are using, many researchers are using those magnets in reactors, high power magnets we can say. So we can increase the value of magnetic field by increasing the current. And straight away you can see the application of superconductivity. And other applications also you can see the power transmission. Nowadays what is happening, some conducting wire has been made of superconducting wires. So because the losses are minimum in case of superconductivity, so once the current start flow in a superconducting wire, it will flow for the many years without any losses. So this is the application. For example, in medical science we are using superconductivity in MRI or in SQUID. SQUID is a device again for measuring SQUID. It is a device, superconducting quantum interface device. With the help of this device we can measure a very small amount of magnetic field, even of the order of 10 raised to the power minus 21. This device can measure a very small amount of magnetic field of the order of 10 raised to the power minus 21 Tesla. Even inside the human body, we have a very small magnetic field inside the tissues. So that amount of magnetic field also can be measured with the help of this device, and it is based on superconductivity. So we have many applications of superconductivity. So now, is the resistivity 0 is the only criteria for superconducting material or something different? Let us talk about this. Electrical resistance, when the electrical resistance becomes 0, when R becomes 0, this is one of the property of superconductor. And the second is, the material should be perfectly diamagnetic. The first one is the resistance should be 0, and the second one is the material should be perfectly diamagnetic. These are two important properties of a superconducting material. If a material is in a superconducting state, then its resistance will be 0 and the material should show the behavior of diamagnetic materials. It is a must condition for all superconducting materials. The electrical resistance, when electrical resistance becomes 0, is not the sufficient criteria for superconducting materials. With this resistance, the material should also follow the diamagnetic property. So that is must condition for superconducting materials. So for example, what happens in the case of diamagnetic materials? This property is explained by Meissner. So there is a very famous experiment, that is Meissner effect. What happens in case of Meissner effect? You can see, if you put a material here in an external magnetic field, then magnetic line of force pass through these materials. Okay, so this is the normal case. Now what will happen here? If we will decrease the temperature and below a certain temperature, this is the case of when T is more than Tc. And this is the case when T is less than Tc. So if we are decreasing the temperature, then below its critical temperature or below its transition temperature, now what will happen? The magnetic line of force will come out from the interior of the materials. So I mean to say here, if you measure the magnetic field, it will be 0. But here in this case, B is not 0. If B is 0 here, So again you can see if B is 0, as we know the very famous formula, B is equals to mu naught H plus I. Now what will happen? I equals to minus H. So I upon H is equals to minus 1. And this I upon H, this ratio is known as the susceptibility. So this is the susceptibility of material. If the susceptibility of material is negative, then the material is known as diamagnetic materials. So it proves again that if any material is showing superconducting behavior, then it must be a diamagnetic materials. So here it is a diamagnetic materials again. So we can say this is the complete information about the superconductivity. If anyone asks you what is superconductivity and what is the definition of superconductivity, how we can explain the superconductivity, so this is the sufficient information by which you can explain the superconductivity, that how the resistance will be 0 and how the material should be perfectly diamagnetic. Next, the classification of superconductor. Classification of superconductor. We can classify the superconductor on the basis of temperature and on the basis of critical fields.